There's something almost poetic about gears. These toothed wheels have been turning the world for centuries, from the first mechanical clocks in medieval Europe to the massive industrial turbines powering our cities today. And right now, we're watching gear manufacturing reach a whole new level of precision. In this clip, we're taking a close look at InvoMilling, an advanced machining method developed by Sandvik Coromant that's transforming how manufacturers produce both spur gears and helical gears. So what exactly is InvoMilling? It's a highly flexible gear cutting process that uses indexable insert milling cutters, meaning the cutting blades can be swapped out and replaced without scrapping the entire tool. That alone saves manufacturers a tremendous amount of money. These cutters are mounted on standard 5-axis CNC machining centers, which most modern shops already own. Here's how it works. The cutter follows a precise involute profile, that's the curved shape of each gear tooth, moving in a coordinated motion across the gear blank. The machine tilts the cutter at a calculated angle to generate the correct tooth geometry. What makes this process remarkable is its flexibility. One set of InvoMilling cutters can produce gears with different numbers of teeth, different pressure angles, and different modules, without changing the tooling setup. Today, we're stepping inside the Zhejiang Ledison Optoelectronics Company Limited facility to watch how LED filaments are born. Ledison is one of China's leading manufacturers of LED filament technology, supplying products to lighting brands around the world. Their process combines advanced materials science with meticulous assembly, and it's genuinely fascinating to watch from start to finish. It all begins with the substrate, a thin strip of sapphire glass or flexible glass, typically just 1.5 millimeters to 2 millimeters wide and incredibly thin. This substrate serves as the backbone of the filament. Using automated die bonding equipment, tiny LED chips, each measuring just fractions of a millimeter, are precisely placed along the length of the substrate at exact intervals. These chips are the heart of the filament. They're what actually produce the light. Once the chips are bonded, the wire bonding stage begins. Ultrafine gold or aluminum wires, thinner than a human hair, are connected from each LED chip to the circuit traces on the substrate. This step requires absolute precision. Even the slightest misalignment can cause a chip to fail. Automated wire bonding machines perform this delicate task at remarkable speed, placing thousands of connections per hour. Next comes the phosphor coating, perhaps the most visually striking part of the process. A carefully formulated phosphor compound is applied over the chips in a controlled dispensing process. This phosphor is what converts the blue light from the LED chips into the warm white light we see in finished bulbs. After coating, the filaments go through a curing oven where the phosphor compound is hardened and bonded. Quality control cameras inspect every filament for coating uniformity, checking that no chips are missed and no air bubbles are trapped in the phosphor layer. The filaments are then tested electrically, powered up individually to verify brightness, color consistency, and forward voltage. Any filament that doesn't meet spec is pulled from the line. From there, the finished filaments are carefully packaged and shipped to bulb manufacturers, where they'll be mounted inside glass envelopes, connected to driver circuits, and eventually find their way into homes and businesses around the world. Welcome to the Hymetis plant of EAS European Ammunition Systems, where 155mm artillery shell casings are born. The machine at the center of this operation is the Umuco 2,000-ton hot forging press. Umuco, a legendary German press manufacturer, built these machines to operate in the most demanding industrial environments imaginable. This particular press stands several stories tall, its massive frame absorbing forces that would tear apart lesser structures. The ram, the moving upper die, travels with precise programmable control, delivering exactly the right amount of force at exactly the right moment. The process begins with steel billets, thick cylindrical sections of high-strength steel alloy, carefully selected to meet military-grade specifications. These billets are loaded into industrial furnaces and heated to forging temperature, typically between 100 degrees Celsius and 250 degrees Celsius, a vivid orange-yellow glow that signals the steel is ready to be shaped. The heated billet is transferred quickly to the press and positioned in the lower die. Then the press descends. In a fraction of a second, 2,000 tons of force compress the steel, forcing it to flow into the shape of the die cavity. This single stroke begins to form the cylindrical body of the 155mm shell casing. The thick walls, the tapered nose profile, the base geometry that must withstand the enormous pressure of propellant gases when the round is fired. Multiple forging stages follow, each refining the shape with successive die sets. Between stages, the part may be reheated to restore its workability. After the final forging stage, the rough casing goes through trimming operations to remove flash, the thin fin of excess metal squeezed out between die halves. What emerges is a near-net-shaped shell body, ready for precision machining to its final dimensions. Strength, density, and dimensional integrity, built in from the very first blow. The UBF112N is a specialized CNC underfloor wheel lathe, a two-spindle machine designed specifically for turning and profiling railroad wheels, both on complete wheel sets and on wheels fitted with new tires. What makes it remarkable is that the wheels don't have to be removed from the axle. The wheel set rolls directly onto the machine on its own rails, and the lathe gets to work. The machine's two cutting turrets approach from either side simultaneously, each carrying precision carbide inserts. Using pre-programmed CNC profiles, the tools trace the exact contour required by railway standards: the tread profile, the flange height, the flange width, the back-to-back distance. The cutting parameters are carefully controlled to achieve the right surface finish, because a wheel that's too rough will wear track faster, and one with incorrect geometry can compromise handling at speed. What sets the UBF112N apart is its ability to handle both reprofiling of worn wheels and the finishing of brand new wheels or wheels fitted with new steel tires, all on the same machine, with quick changeover between programs. In a busy rail maintenance depot, that flexibility means more wheel sets turned per shift, less downtime, and trains back in service faster. Precision engineering in service of keeping the world moving. Now here's a process that really showcases the marriage of power and precision. Rolling a 20mm thick steel plate into a perfect cylinder is no small feat. That's nearly an inch of solid steel we're talking about. The 4-roll plate rolling machine makes it look easy, but there's some serious engineering at work here. The 4-roll configuration is a game changer, and here's why. That top roll doesn't just push down. It's powered and actually helps drive the plate through. The bottom 3 rolls work in perfect harmony, with the 2 side rolls being independently adjustable. This gives you control that was simply impossible back in the old days. The process starts with heating. 20mm plate needs to reach about 1,800 degrees Fahrenheit for optimal forming. Too cold and you'll crack the steel. Too hot and you'll alter its metallurgical properties. Temperature sensors monitor this constantly, ensuring we're in that sweet spot. Watch as the glowing plate enters the machine. The operator, and these folks are true craftsmen, adjusts the roll positions using hydraulic controls that can apply up to 500 tons of pressure. That's the weight of 5 fully loaded tractor trailers pressing down. The plate begins its first pass, curving slightly. Then it rolls back through, each pass bending it a bit more. The beauty of the 4-roll system is the pre-bending capability. Those side rolls can lift and curl the plate ends before the main rolling begins, eliminating the flat spots that plagued older 3-roll machines. This means less finishing work and tighter tolerances. Hydraulic systems maintain constant pressure as the plate thickness varies, because even in uniform plate there can be variations of a few thousandths. Computer controls adjust instantaneously, something a manual operator simply couldn't do. After several passes, that flat plate has become a perfect cylinder, ready for the longitudinal seam weld. The precision is remarkable. You can achieve diameter tolerances within a quarter inch on pipes 10 feet across. Bending 56mm steel plate is not a job for the faint of heart or an underpowered machine. What you're watching here is a heavy-duty hydraulic press brake working through a thick steel plate with impressive control. The tooling, a precision V-die and punch, is selected to match the material thickness and the desired bend radius. The machine's back gauge positions the plate with repeatable accuracy, ensuring each bend lands exactly where it needs to. As the ram descends, the hydraulic system delivers thousands of tons of force, forcing the steel to yield and conform to the die. The result is a clean, accurate bend. No springback surprises, just solid, formed steel ready for the next stage of fabrication.